We've made a thing. It is this thing. This is the thing that looks like it tells you whether that's stable or unstable, stable or unstable. Something glittery about it, and we can also change the formula, and we get all sorts of nice different shapes. That's a nice shape. What sort of shape is that? Well, it's stable, unstable, stable, unstable. These are Julia sets, or rather the boundaries, which are Julia sets. Sets of stability and instability on the complex plane, all intimately tied up with the Mandelbrot set, which we're going to get to. But first we need to build these things, which are the Julia sets. And that's what we're going to do in this video. Right, it's the new year, and therefore it's time to fulfill some promises that I made in other videos on this channel. I said repeatedly that I want to do an exploration of how I would demonstrate the construction of the Mandelbrot set. And I particularly mentioned that when we were doing the bifurcation diagram stuff, which is intimately connected with the Mandelbrot set. So we're going to do that now. I'm actually going to split this into two videos, though. I'm going to do some work on the Julia set, which is obviously a good way into the Mandelbrot set if you know anything of the story, and hopefully you will, even if you don't already, if you watch this. But I should say that this is really going to make much more sense if you see the video I'm doing now in the context of at least two other videos. One is the number file video I did quite some time ago with Brady on the number file channel about the Mandelbrot set, and that's where I use the files that I'm going to build in a way that I regularly do in talks around the world when I'm talking about this stuff. So I did that on the number file channel already, and check that video out. That's where I use the files that I'm going to build. I'm also going to direct you to another video which is absolutely excellent exploration of some more deep mathematics behind this, the complex numbers holomorphic functions, from Grant Sanderson, 3 blue 1 brown, and he mentions the file that I'm eventually going to build here in his video, which I'll link on the screen here as well. It'll also be in the description. So I said we're going to split it into two. We're going to focus on building the orbits of a complex iteration, and that will help us visualize both a Julia set, whatever that is, and eventually the Mandelbrot set. Neither of these are particularly hard to code, but like all things, they're easy when you know how, and surprisingly beautiful. So there's two things I'm going to do in this video. One is we're going to build the orbits of a complex iteration that will get us some convergent or divergent behavior. And then we're going to kind of do a neat little trick, which is kind of the nice punchline of this video, to get the boundary of that behavior, which is going to be the Julia set itself. And then we can tweak that idea that we've got to do the Mandelbrot set. But I'll probably park that into another video. So let's go to the Julia set now. Okay, so I'm looking at a Geogebra Classic 5 window, as ever. Starting from complete scratch, first things first, I can put a dot on the screen and it's a point, but I could change this properties of this point, and if I pop into the the algebra section, I can say, please treat this as a complex number. So GeoGebra handles complex numbers, and this is dynamic, and you can move it around. Great. There's the number up there. There is an easy way to do that. You could just get the complex number tool, which is in the point menu, drop down, click complex number, and then it names it in a more complex numbery convention. Actually, I want a point called A. That's going to be the starting point of my iteration, and I want another point called C. So I'm going to rename this to be C. And if you are at all thinking, that's the C, this is from the famous function we're going to work with in these two videos, z squared plus C. That's the function we're going to iterate to see what its behavior is. And there's a complex function, but it needs a C that's already defined, which is a complex number. So let's define that function now. I'm going to call it f, just because I'm going to call f of z. I could use any letter in there. It's a dummy variable, but that's traditional to do that with complex numbers, as you can see on the complex number button up there, obviously. The function is z squared plus c. Now, since it already knows what c is, and it recognizes that c is a complex number, when I define this, it's going to realize that it's a complex valued function. If you don't believe me, if I right click on it, it says complex function. It's also not plotting it. If I typed in a real valued function, it would plot it. If I typed in g of x equals x squared, did I not type that properly? X squared is prettier. Let's do that. Obviously, it plots it, and you can turn it off or on. But with a complex one, it doesn't plot it. Now, you can tell it to show you what's going on, and it draws these things. I'm not going to explore what that means in this video, but it is nice that there is an inherent way of just showing what the complex function is doing. Go and explore that. I was slightly surprised when I realized Geogebra did that, because I'd forgotten entirely. So I'll explore that another time. For now, though, I've just got a function. It is z squared plus c. It's the simplest quadratic function with a parameter, by some way of arguing that. And the parameter is c, and the starting seed, if you like, is called a. And actually, those two words are going to come back to haunt us when we convert from Julia to Mandelbrot sets. More on that later. So what are we looking at here? Well, I want to iterate this function. And last time we talked about iteration of the bifurcation diagram, there was this great command called iteration list. And it's fine here, right? I could just use the function f. I could start with a and say do 10 iterations, but we have an issue, which is the iteration list command in Geogebra doesn't seem to like complex functions, which is why it says it's an illegal argument. I don't know why that is, but it means we can't use this command to get a neat way of generating a list of iteratives. However, built into Geogebra is a very traditional way of iterating some tedious tasks, which is a spreadsheet. And it's just built into Geogebra. I think I demoed this on the bifurcation diagram video as well. So I can use this to iterate in a very simple way. And in some ways it has some advantages. In other ways it's a little bit less neat. However, I'm just going to say the first cell to be my seed, A. You can say it equals A, and it's just put that number in there. And that will change with it as it moves. And then I'm just going to iterate it by saying do f of the previous cell, A1. And then copy that down. So let's do a few iterations. I don't know how many we'll need. Let's go up to 100 because it seems like a nice round number. Very quickly, this has gone off to infinity, and you think, well, it'd be nice if it plotted these. It has plotted them. They're just off the screen. So if I bring this back in close, you can see those iterative points are on the screen. Now, I don't want the labels, so I'm just going to right-click on the whole column here, turn the labels off. Useful way to select lots of things in the spreadsheet. I'm going to turn off the first two cells because that will be A, and that actually will be C. Is that right? No, it depends what A is. I'm going to turn these off anyway. And you'll still be able to see that we can move these things around. Why can't I drag that? Does that matter? I want to be able to drag A. It's not letting me drag. Why is that? Strange. I had come across this glitch recently. Anyway, I'm dragging A around. I've got the points. They're not labeled anymore. Already we have the orbits of this iteration. And it's handling with zeros quite well. And if it goes off to infinity, it handles that okay without too many problems. And you can see that sometimes it heads towards 0 and sometimes it heads to infinity. And it's relatively clear where the boundary is. It looks like if you go beyond 1 away from the center, in fact, if we just visualize that, let's draw the circle manually. Center 0, radius 1. The unit circle is the boundary. You drag A, you go inside and it's stable, heading towards 0, and outside unstable. It would be nice if we could join these points together to see how the orbit bounces around. And that's easy to do on the spreadsheet as well. I'm just going to use the next column. Let's say equals a segment. And here's a Geogebra comment actually. When I'm typing formulas into the spreadsheet, it doesn't autocomplete, which is really annoying. I use autocomplete to figure out what functions exist. But that's just an option you can turn on if you go to spreadsheet options and then use autocomplete. I need to do this regularly. Now if I type segment, it's like, oh, there we go. Now you can't use tab to jump between arguments because it moves cell then, but you can still do it. So I'm going to join the last 2 points together. So segment from A2, let's go from A1. Oh, I used tab, didn't I? A segment from A1 to A2. Hopefully it now recognizes this as a command. There we go. Now it's drawn it, and I can copy that down. And it's drawn all the segments again. It's put labels on. Let's just turn them off. And now I've got a better visual. Let's zoom in a bit, shall we? This is clearly the important bit. That's the orbit. It's nicely convergent onto 0 unless I go near the circle edge, in which case it's still converging. If I go over the edge, unstable. So already this is a nice way of visualizing iteration. Actually, if I get on the circle, now that point is actually on the circle. And the orbit is showing it bouncing around on the circle, but I think there's a rounding error. This is a computational issue that eventually the iteration detects that we're slightly off the circle because of a tiny rounding error, and then it starts diverging and it's shooting off to infinity. Probably the same up here. That's quite entertaining behavior. I'm not quite sure why I'm seeing a sort of cardioid shape in there. More to investigate there. What I'm showing here, though, is a quick way of demonstrating orbits. It's really nice and smooth, convergent, divergent, stable, unstable. Now the real catch is at the moment I've left C as 0, it's in the middle, and if C is not 0, can I move C around? Then we get different behavior. And this time the boundary is clearly not a circle because I'm inside the circle and it's unstable, whereas here I'm outside the circle and it's stable, heading towards that point in there. So the circle is actually kind of meaningless now. Let's turn that off. And I'm still getting this glitch about why I can't drag this point. I'm a bit puzzled about it. Anyway, so that's the orbit. I'm going to reset C to 0 and say actually what would be nice is to know the boundaries of the stability of these orbits. And that's a different question, which we can also solve by a really neat bit of mathematics. So I'm going to stay on the same Geogebra file. I'm actually going to hide the things we've got here. So I'm going to hide these two columns. Show all the objects. Yeah, that's showing them. That's not showing them. I don't know why it's highlighting different objects. They're not shown now. Okay, they're all gone anyway. And I'm going to actually insert some columns. Insert left, because you can do that. I could scroll to the right, but I'm just going to insert them. And we might need more space. We can turn those columns back on if you want to see both behaviors. However, what I want to do is show the boundaries of when I move the C around, what different shapes other than a circle we get. And the reason that's hard is that they are repelling boundaries. And if I do turn these things back on, I'll show you what I mean. When I'm near the boundary, on one side it heads towards 0, but if I go the other side of the boundary there, it heads towards infinity. And so the boundary is where things sort of fall off a cliff. Anything near the boundary actually ends up moving away from the boundary. It's a repelling set of points. What I'd like to make them into is an attracting set of points, because then I could pretty much put a random point iterator and it will get attracted to that boundary. Now, to go naively on this, the opposite of repelling is attracting. So I need the opposite function. I need the inverse function to do that. And if I work this function backwards, all the points that repel should become attracting points, because we should go backwards down that iteration. And so maybe think of it as the boundary originally was a sort of mountaintop and everything sort of rolls away from either side. If I can make it inverted and become a valley, then everything will fall into it. That's my plan. So let's hide these things again, and we'll start with a new idea. So I'm going to get the inverse function. Now, there is an invert function in GeoGebra. Invert function, yes, brilliant, please. We have the same problem with a complex valued function, though. So I can't just do it by automatically. It's relatively easy to invert. Let's call it g of z for the inverse. To invert z squared plus c, you need to take away c. So z take away c, and then all of that needs to get square rooted. And we have some complications here, because we're trying to square root a complex number, and that is potentially problematic. To realize, I just wanted to hide that point. It was showing up on top of my A. Square rooting in complex numbers is multi-valued, just like it is in real numbers. So we get around that in real numbers by just saying, just take the positive one. It's less obvious what to do in complex numbers, and in fact, quite a deep issue. Let me show you what I mean. Let's use a different set of points. So in these columns now, I'm gonna do the iterations. I'm gonna start with A again, and we're gonna iterate the g of z, g of a1. That's what we're gonna do. And at the moment, c is still 0. So when we get the boundary, we should be getting a circle. And you can see that that's done that number, take away c, and then square root it. And it's only giving me one answer. It's taking the positive root. And for a complete picture, I'd need the two solutions. There'd be another one 180 degrees, in fact, over there. The trouble is, if I kept iterating that, we'd have an exponential explosion of points. We would go from 1 point to 2 points to 4 points to 8 points to 16 points to 32 points to a lot of points very quickly. And it would be actually difficult to figure out how to do that on a spreadsheet or in a list, in fact. Now, you can do that with other software, sure, but I just want to find a way of doing it quickly in GeoGebra. But nevertheless, let's iterate all the positive square roots. Let's drag this down. I don't know, let's do 100 again-ish. Doesn't really matter. You see this is converging. You can see what it is being an attractive point. So wherever I start, it seems to converge onto 1 there. But there is a bit of a jump. This is to do with how do you choose which square root to do, and to do with cuts in the complex plane. And I'm not going to go into the details here. What I really want to do, though, is get the other points, which could be attracting points or repelling points in the original version, which is the rest of that circle. And the reason we're not picking all of that up is that we're only ever taking the positive square root. So without exploding exponentially many points, let's just find another way of making sure we've got a variation between positive and negative square roots by picking at random whether to do the positive or negative square root each time. And I think what you'll see is that these points then become less obviously convergent on that point, and they'll spread themselves around the attracting basin of points. To do that, I'm going to just put a number next to them, which is going to be either 1 or -1. The easiest way to do that perhaps is get a random element. It's a random element. Just needs a list, and it will pick a random element from the list. Random element, curly braces for the list, and in the list I want 1 or -1. And there it is, it's picked 1, and if I copy that down, we'll get a bunch of 1s or negative 1s. That's straightforward. And actually what I want to do is change the iteration here to be multiplied by the number over here. So pick a random 1 or a square root, or a -1. So that's B3 there. Have I missed a cell at the top? I have. Copy that one up. Copy that one to there. Copy that one to there. And copy this down. Double clicking it seemed to break it. Let's just grab that and copy it down. No idea why that broke. It broke again. Okay. I was having some weird issues with some glitches there. The plan is to just multiply the iteration by there. So I'm just going to, I've deleted all the other things I've already generated. I'm just going to copy down from scratch again here. So let's just copy that. And we'll drop down to all the way to 100. It's got to be a better way, Ben. Never mind. I've done it now. Paste. Right. Now we have a circle. Look at that. We have the old things over here are not showing on the screen, but we have attracting points. And you can see that wherever I start the seed, like the first few iterations bounce around a bit. I think it goes there, there, there. It ends up falling into the circle. Now what we could do is make sure that whenever we move something around, like A or C, that we update the random numbers, and we'll actually get these things moving around, blinking, and actually we might get a bit more of an illusion of what the shape actually is. So let's check that. On any object you can have an onUpdate script, and I'm just going to do an update construction command, which is a sort of really heavy-handed way of forcing everything to get recalculated. It's going to redraw on the entire construction and recalculate any random numbers. I think that's a bit like pressing F9 on an Excel spreadsheet. And now you get this sort of glittery effect. The randomness recalculates every time, but we do get a very good, strong illusion of the circle. Let's do the same for point C before we move it around. Update construction. I think I spelled that wrong. Yes, I did. Just where my mouse pointer was. But let's also hide the first few iterations. The first 5 or so are the ones that sort of bounce, don't sort of converge to the attracting boundary first. So let's just hide the first few of them. Turn them off. I've still got A. And now if I move C, I should get a pretty good image of the boundaries of these points. And that's the magic. That's really nice. It's kind of glittery and sparse, and it's not a full drawing, but these are, after all, fractal shapes. These points are the Julia set. The Julia set, Grant talks about this really nicely in his video. The Julia set is not the inside of that shape, nor is it the outside. It has actually that set, and I was confused about that a long time. Now, these are not the only Julia sets. You can have different functions. It's not just the z squared plus c. You can use any function, you can get a Julia set of it. And again, watch Grant's video for some more discussion of the misconceptions that several of us have had when we learn about these things. But this is kind of the guy. I actually don't really want to have A. It doesn't really matter where A is. You can see that wherever it is, it converges to the boundaries. So I'm going to leave that sort of off shot. And in fact, we could just hide it. And it's moving C around in this formula that changes what the boundaries of stability are. So there we go. Now, what would be nice is if we can see the orbits as well, then maybe the A is important if we want to see the orbits. So let's bring A back in and turn these columns back on. That's clearly divergent. I'm going to hide the first 2 just because they sort of get in the way of A and C. And now you can see that with this, the boundaries there glittering away, divergent, unstable, stable, unstable, stable. And if I change C, that's nice. Stable, unstable, stable, unstable, stable, unstable. And so the boundary of the stability and instability is what they call the Julia set for this function. Now we can use this because we're almost ready to plot a Mandelbrot set style thing, although there's some complications with actually plotting the boundary of the Mandelbrot set, but we can still do some useful things in Geogebra on it. Already this is really fun to play with, whether you want the orbits or the boundaries. And I really like that neat trick of using a random element to get the sort of approximation of the attracting points. When I first saw this done, it was done in Geometry Sketchpad, and you couldn't use a spreadsheet along Geometry Sketchpad. You could do some basic calculations, but it did have an iteration command. So it actually did the full iteration, but it got the square root business by geometrically halving the argument and square rooting the radius. It did it geometrically, which is the lovely thing about complex numbers. So fair play to the people who did a demo file in Geometry Sketchpad all those years ago for where we got the principle of how to do this, where I got the principle from. And let me give a hat tip to Colin Wright, who was the one that suggested to me the idea of randomizing the plus or minus 1 in order to get an approximation here, in order to get a quick, dirty demonstration of where the boundary is. We have to do a couple of tweaks to get what the Mandelbrot set is as opposed to the Julia sets here, and we'll do that in the next video. In the meantime, if you haven't done already, go and watch the number file video where I use this file, and go and watch Grant's video explaining what the maths is all about, and I'll see you next time.